Hey, good whatever time of day it is. This is the day we're going to start talking about derivatives, and we're going to start with a formula. Some people say this is the most important formula in calculus. That's great. Formulas have a lot of information packed into a few symbols, so they really take some explanation and practice. So, first of all, let's just practice reading this. This is a limit for h near zero. Everyone around you is going to say h is going to zero. H isn't going anywhere. It's just near zero. It's just hanging around. And it's a limit of a fraction. And this is a fraction that you've seen before. If you take the limit away, this is the average rate of change of the function. And the bottom of the fraction is h. And the top is these two values of the function. One's at x, that's the point that we're interested in, and the other is we've just moved it over a little bit because h is just hanging around. So we've got this difference of two values, that's the change in y, and on the bottom we have the change in x. So I'm going to write this right away as approximately the change in y and the change in x. So this is the start of explaining the formula. It's seen, what else that you can do with it. The notation here, f prime of x, is one of the many notations for what's called the derivative. And it's an interesting notation in that, okay, it's something to do with the function f, but it's not the function f, so we better put something else in there to distinguish it. So it's f prime. It's derived from f, and that's the formula for it. This is not an important formula in Math 1160. This approximation is what's important. And so, nonetheless, we have to do this a little bit. Let me tell you where the danger point is. And the danger point for almost everybody, if you start to do the algebra, is in looking at f of x plus h. So the thing is, f is what it does. The function is what it does. The formula is what it does to x. But now you do whatever that was to x plus h. So we saw this the other day in that if f of x is x squared, f of x plus h is just, well, you just copy and paste. And if f of x is 1 over x, then f of x plus h, do the parentheses first, it's a fraction. And what's going to go on the bottom? Well, in this function expression, the input goes on the bottom. So in this function expression, the input goes on the bottom. So we just put that there. And then you worry about doing the simplification. Do the parentheses first. Input's on the bottom. Okay. There are a bunch of special formulas with this I'm going to get to at the end today, but and you do need to see their derivation. This is all written down in my book and in Hughes Hallett in my book. It's in this chapter, sorry, and you can see all the algebra that you want, which is probably more than you want. But you do need to be convinced that this is something that has some truth value to it. It's not just some formula that someone picked out from behind their ear. There's some reasoning behind it, and the reasoning's pretty good. Okay. So the big deal behind this is I'm going to write down that difference quotient again. So it's a fraction, h is on the bottom, and we've got the two values of f on top. We've got their difference. And so the derivative is the limit of this. So that means that the derivative is near this when h is near 0. And so this is approximately f prime of x. Bingo. Now we've got something going for us here because f prime of x is something that we can find using algebra. And what we have over here is, as I've already said, it's the change of y divided by the change in x. And so what you're seeing here, I'm just going to write this another way, is that the change in y is approximately f prime of x times the change in x. So I'm going to do this in colors and emphasize it. And this is it. This is calculus right here. This is calculus. And so what we have here is the tangent line approximation that we already talked about. But now we know the slope of the tangent exactly once we found the derivative. And so this is a useful thing for us to have had. And so now we're much more precise about it. The problem is in finding the derivatives. So let me give you a little table of derivatives. And this is all in all the books. And I'm going to be very general about this. If f of x is x to a power, pretty common kind of function, then the derivative of that is what you do is you multiply by the power and then you subtract 1 from the power. There are justifications for this everywhere. It's in my book. If someone demands it, I'll go through it, but it's a fair amount of algebra. We did it with 2 the other day, so this isn't completely foreign. And there's a way that people mess this up. So if you want to take, say, the derivative of x to the 1/2, square root of x. So that would be one way of writing it, is you just put the expression for the function and then make a prime. And everyone tries to get fancy and do stuff in their head. Don't do algebra in your head. Don't do algebra in your head. Don't skip steps. And what everyone does is try to skip steps here. We're not going to skip some steps, so I'm going to show you what happens here, is that you multiply by the power, and then you subtract 1 from the power. That's it. That's what you do. You multiply by the power, and then you subtract 1 from the power. That's the derivative. Now, you can rearrange this in various ways to make it possibly more useful, but that's the derivative. If you do this step, then you won't get these wrong. Just as another example, x to the minus 1, well, that's a fancy way of writing 1 over x, but I'm going to write it as x to the minus 1. If you want to take the derivative, you multiply by the power and then subtract 1 from the power. Don't skip this step. Everyone skips this step. That's wrong. You'll get it wrong. Do this, then start doing the arithmetic. Especially with the fractional powers, it's really easy to get this new power wrong. So don't do it. Okay. Now, the other big derivative rules are, so we've done powers. That also takes care of square roots. It takes care of 1 over x. Takes care of all kinds of useful stuff. And so that's fine. There's another one, the derivative of e to the x. This is like one of the most important statements in the history of civilization. The derivative of e to the x is just e to the x. That's what makes e natural. The derivative of e to the x is e to the x. This is the key to so many models and so many applications. And so this is just a very, very important thing to know off the top of your head, because it is really one of the most important things that civilization has ever discovered, even on Venus. Okay, now once we talked about exponential, we've got to talk about logarithm. And if we take the natural log of x and we take its derivative, that comes out to be 1 over x. We can go into more detail about this one because this is something that you can discover with a calculator. But this is something you just got to know. Okay, and the last one, which is in my book but not in the well, it is in the Hughes Hallett text. The derivative of sine x is cosine of x. Cosine of x is the same thing as sine of x minus pi over 2. And so this is also one of the most important things that has been discovered in civilization. So this one especially, this is what what connects calculus to reality. And so, so here it is. Here's our tangent line approximation. It's now much more exact because we know how to find some of these derivatives. And here are the basic rules for taking derivatives. and you can get a lot more practice with that. But in this course, we don't do a lot of taking derivatives by algebra. What we're more interested in, this guy right here, the tangent line approximation. Now we can do this, you can find square root of 65 or something if you like, or natural log of 12 or 13 if you like. Big woo. When we start working with models, using this tangent line approximation is one of the most important things for taking information from a model and putting it together and getting something useful out of it. And so what we really want to do is use this hundreds of times, not once. But anyway, this derivative is what goes into it. These are the basic rules. This is why we're doing it. And have a good weekend.